Hello, everybody. We are Team 23042, and we are working on the Tabletop Silage Additive Research System, aka the SAR system. We are sponsored by the University of Arizona Biosystems Engineering Department and Dr. Duarte Diaz and Brian Little. So who are we? My name is Eric Jekate. I am a Biosystems Engineering major, and I am the team lead of this project.
My name is Kenyon Cook. I'm a mechanical engineering major, and I'm the mechanical lead for this project.
We also have another teammate named Martin Calderon. He is a mechanical engineering major as well, and he is the research lead of this project.
I'm Alex Hillman. I'm in electrical and computer engineering, and I'm the procurement lead.
I'm Fahed Al-Rashid. I'm the electrical lead, and I'm also an electrical and computer engineering major.
So what is silage? Silage is a mixture of fermented corn, wheat, grass, and cereal grains that are put in fermentation conditions and used to feed livestock during times of low pasture and drought. This is also used to supplement their diet during normal conditions due to the digestive aid that it provides to the cattle. Silage accounts for a significant amount of spending in the livestock industry because it is very important that the cattle are healthy and well fed even during times of low pasture or dead grass. So the current methods of silage additive research are to have two groups, one a control and one a test. And similar to any other experiment, you would put your additives into the test category and keep the controls the same. You'd seal both sets of bags and leave them for a set time. After this set time, you would open one control and one test, and you would run your experiments to see the vital measurements that you need. And then, but after you do that, the bags need to be discarded and the silage is now spoiled because fermentation is an anaerobic process that cannot allow oxygen to re-enter the system. So basically, this system is very wasteful and this method should not be used anymore. So the issue at hand is that current silage additive testing methods are very inefficient. There's massive waste of silage resources. It's prone to human error if you don't seal the bags properly or you take a bad measurement because there's no going back once you open the bag. And then there's also no method of continuous data collection since this is only at certain time points throughout the overall span, and you don't have access to the data at all moments. Spoilage can mean farmers miss out on millions of dollars worth of product and cannot feed their herd the right way. So our main goals when designing this system were to create a system capable of successfully facilitating silage fermentation, to successfully record and upload sensor data throughout the fermentation process, facilitate easy access to recorded data from each experiment, and allow for easy maintenance and operation going forward. So our system requirements are broken down into four main sections: the sensors, the output, the physical, and the electrical outputs of the system. So our first requirement was that the system facilitates successful fermentation. The second requirement was that the system must record pH, temperature, oxygen, VOC concentration, which includes ethanol and ammonia, and then also record the humidity. The system shall fit within a 3x3x3 cube, weigh less than 50 pounds, and be powered by a standard US wall outlet. The system interface shall enable users to extract output data, reset the system, and start the fermentation cycle. The data should also be output to a web browser accessible remotely by the researcher. The system shall be easy to transport and resistant to high or low pH, temperature, and environments. And then also the system shall be able to operate for extended periods of time without maintenance or user input because fermentation is a long process.
I'll be talking about our system block diagram. So starting from the middle, we have our Raspberry Pi. It's in charge of our main system status and processes. And to the top of our Raspberry Pi, we have our push buttons and LEDs. These are connected through GPIO pins, and they'll give our researchers quick status updates on what the system is doing right now and how to interact with the system. To the bottom, we have our power switch and power supply. These just provide power to our system. To the right of our Raspberry Pi, we have our sensor subsystem, which consists of our VOC and O2 sensors, temperature and humidity sensors, and our pH sensors. These are directly connected to our fermentation chamber, which also includes an airlock to prevent positive pressure from building up and allows outgassing to atmosphere. To the very left, we have our GitHub repository. This is where the Raspberry Pi will output its data to. It'll also be our researcher is going to interact with the data that our system will be outputting. And we also have the standard US power outlet, which will provide power to the power supply.
This is the Czar system. The Czar system is built around an off-the-shelf pressure cooker that has been modified to ferment and analyze live silage. We chose a pressure cooker as a base due to its durability, ease of access, and ease of cleaning. Integrated into this base is our sensor suite, electrical housing, and mechanical subsystem. The sensors are primarily integrated into the lid of the system, with the exception of the pH probe, which is inserted into the side due to the pH sensor's requirement to be submerged. This protects the sensors from impacts and allows for easy inspection and maintenance. The electrical housing sits atop the lid of the system as well. Here it is safe from impacts and has quick, easy access to the majority of the sensor suite without the need of excessive cabling. The electrical assembly features a suite of multicolor LEDs for quick debugging, a power switch, a start-stop button, an integrated cooling fan, and a Raspberry Pi. The Raspberry Pi makes up the brains of the system and is continuously connected to the UA Wi-Fi, constantly uploading the sensor data to a GitHub repository. This allows for quick and easy access to the data from a remote location. All it is required is access to the internet and a Windows 10 operating system. The remainder of the mechanical subsystem includes a liquid airlock to prevent buildup of pressure, external handholds for ease of transport, and the fermenter body itself. Overall, this design emphasizes simplicity and robustness with easy-to-replace components and a lack of needless complexity.
Pictured on the screen is the user interface for the TSAR system. This is a GitHub repository, which is maintained by the Raspberry Pi inside the system. As you can see, the Raspberry Pi manages the layout of the repository, which includes experiments as well as runtime characteristics of current experiments, which would include, the experiment start time, stop time, the current runtime, as well as like data characteristics such as the pH trends, as well as other trends such as the oxygen content over time, which would stay relatively low or actually at zero, as well as allowing the researcher to download data at different points. If they choose to download data from the current experiment or from past experiments, it is all there and kept online as well as locally stored onto the Raspberry Pi. And that will allow the researcher constant access as long as they have a Windows 10 device or similar kind of smartphone operating system with access to the internet.
So why we chose our system? We had the choice between aluminum, glass, and plastic. We previously determined that a cylindrical design would be the most efficient. So our main factors were price, durability, the ability to handle pressure, the corrosion resistance, odor resistance, ease of sterilization, and ease of fabrication of the system. So as you can see, the points are here, and the aluminum came out on top, which also happened to be a blessing because that is also the material that off-the-shelf pressure cookers are made out of. And so that was the main reason why we chose our chamber housing. So finally, we would like to thank the University of Arizona Biosystems Engineering Department for all of their support, funding, and the opportunity to carry out this project. We would like to give a special thank you to our sponsors that we work directly with, Dr. Duarte Diaz and Brian Little, for all of their support and input along the way. We would also like to give a big thank you to Mike Mason at the BE Fab Shop for all of his advice, tools, and know-how. And lastly, and certainly not least, we'd like to thank our sponsor, or our mentor, Mike Majerick, for all of his help teaching us the engineering process and what it takes to succeed in this industry. Thank you.